Hello and welcome back. The purpose of this video is to derive Bernoullis equation, which will be one of the two fluid dynamics equations that we look at this semester. So we've drawn a pipe at this location, and then we've done the derivation on this side of the board, and it looks like a lot of stuff. Please don't be overwhelmed. We're going to go over everything slowly. So beginning with our pipe, notice that we start off with a pipe that has an area A1 down here, a cross-sectional area that's large, and then our pipe is changing height and tapering down simultaneously. And when we get up here to this location, at this location, the area of the pipe is area A2. In addition, the pressure down here is P1 and the pressure up here is P2. And notice that I've drawn these dashed lines. So from this line to this line is the fluid of mass M that is confined within this zone at time t equals 0. So we have some mass M of fluid, which I've shaded here in yellow, that goes from this location to this location. It is confined within these two endpoints right here at time t equals 0. And then we allow the fluid to flow, and at some later time, now the fluid is confined within these two endpoints of the pipe. So that same mass M now is confined within these two endpoints. So this whole derivation is going to be based on conservation of mass. Those molecules that make up our mass M have to go somewhere. And so that mass M that was being confined in this section of the pipe is now going to be confined in this section of pipe at some later time. So our beginning point is going to be right here with the work energy theorem, which, as I advertised when I first introduced it, is an incredibly useful formula that is widely used, and it's a scalar equation, so it's quite nice to use, and we're going to start with this particular equation. So when we look at this equation, we need to look at the work done on our mass M as the mass M moves from being confined between these two spots to being confined between these two spots. So what entities are doing work? Well, the mass M is in a gravitational field, and the Earth pulls on all molecules. Therefore, there's going to be work done by gravity, as there are forces being exerted by gravity. In addition, our fluid is in contact with fluid to the left. Notice that the fluid to the left is pushing in the same direction as the fluid is moving. As the fluid moves this distance x1, simultaneously, the fluid that is to the right in the pipe is pushing backward on our mass M as it moves this distance x2. So there's work being done by pressure forces in addition to work being done by gravity. So we have two works that are being done on our mass M, and so the sum of those two works makes up our network, and that's equal to the change in the kinetic energy. So writing the change in kinetic energy is fairly easy. Notice that from this location to this location, this part of our mass, notice this isn't all of our mass, but this part of our mass does not change speed, and it also does not change height. Okay, but this little chunk right here, notice that if I took this little chunk of delta M, which delta M is the density here, rho 1 times the volume of this fluid V1. If I took this and moved it up here, I would have that same delta M, as this section right here doesn't change at all between these two times. So this little chunk right here is the piece that comes up right here and is now the same delta M, which can be written as the density at this location, rho 2, times the volume V2. So these delta M's are the same. So the only speed that's changing is the speed of this fluid right here. This little chunk right here is changing speed from this location to this location, while this fluid that is confined here does not change. So the change in kinetic energy then can be written as 1/2 delta M That's this chunk times the speed at this location squared minus 1/2 delta m, that's that chunk right there, times v1 squared. So that's our change in kinetic energy. Now, what about the work done by gravity? Well, remember, gravity is a conservative force. Therefore, I can write the work done by conservative forces as the negative of the change in the potential energy. So we are going to be looking at that in a moment, but the next thing, work done by pressure forces, well, this is going to be pretty easy to write because we have some force F1 that is being exerted by the fluid that is not part of our mass M, but is to the left. So it's pushing our fluid of mass M along this distance x1 as the fluid that's up here to the right of our confined M is pushing backward against our mass M as it moves this distance x1. So the fluid that's to the left is doing positive work as our mass moves this distance x1. So that's going to be F1, the force being exerted by the fluid that's to the left of our mass M, times x1. And now the work being done by the fluid that's to the right of our mass M is doing negative work because the force is being exerted by the fluid that is not part of our mass M but is to the right is pushing backward, hence the negative sign. And it's exerting a force F2 for that distance x2 that we are looking at the movement of our mass M. So now we're going to write F1 in terms of pressure and area. Remember that pressure is equal to force divided by area, so force then is pressure times area. So I can rewrite F1 as P1 times A1 times that distance x1, minus, now I can write F2 as P2 A2 times that distance x2. Now notice that A1 times x1, if I take this cross-sectional area and I multiply it by this length x1, I can write that as the volume V1. And then I can also write A2 times this distance x2 as volume V2. So this confined volume, this volume right here, which I'll polka dot right here, this volume right here is volume V1, and this polka dotted volume right here is volume V2. All right, so we have the work done by the pressure forces, and we're going to use exactly this expression. So now let's work on the work done by gravity. Okay, so the work done by gravity, again, look at this location to this location. As the fluid moves from being confined between these two spots to being confined between these two spots, this chunk right here does not change height. It does not change height. The only part that's changing height is this chunk of fluid right here, delta M. This little chunk, delta M, is being lifted up to confine this little, to be confined in this little chunk, delta M. So the only piece of the fluid that is actually experiencing a change in its potential energy is this little chunk right here. So the work done by gravity then is the negative of the change in potential energy. So this is minus, open parentheses, the final potential energy. The final potential energy is that little chunk delta M times G times the final height minus the initial potential energy. The initial potential energies are little delta M times the acceleration due to Earth's gravity times the initial height. And remember, we've got that negative sign out in front. So now we're going to write delta M in terms of density and volume. So we have our minus, open parentheses, delta M at location 2 is rho 2 V2 times GY2. Minus our delta M at position 1 is rho 1 V1 GY1. And now we're going to distribute the negative sign through the parentheses, and when we do, the second term becomes positive and the first term becomes a negative, and so this is just rearranged. Now we're going to plug everything in to our work energy equation because now we have all of our terms. So The work done by gravity. The work done by gravity, remember we have right here, so we're going to plug it in, rho 1 v1 gy1 minus rho 2 v2 gy2. Now we want the work done by the pressure forces next. The work done by the pressure forces is here, so plus P1 V1 minus P2 V2. And now we want to set that equal to the change in the kinetic energy. Here is the change in the kinetic energy, so 1/2 delta mv2 squared minus 1/2 delta, I'm missing the delta sign, I apologize. So this is going to be minus 1/2 delta mv1 squared. So there's our equation. Now we're just going to rewrite it here. So notice that all these terms are the same. And now on the right-hand side, I'm just writing in delta m at location 2 as rho 2 v2, and delta m at location 1 as rho 1 v1. This is Bernoulli's equation where we have compressible fluids. So this is Bernoulli's equation for compressible fluids. Compressible fluids are gases. We are not going to be dealing with compressible fluids. We are going to only be dealing with incompressible fluids. Okay? Compressible fluids have the ability to change their densities, where incompressible fluids do not change their densities. So if it's incompressible, then that means that the densities at location 1 and location 2 are the same. And if the densities are the same, then the volumes are also the same. So notice that the only way delta m's can be the same here if the densities are the same is if the volumes are also the same. So I can set V1 equal to V2, and I can set rho 1 equal to rho 2 equal to just rho. Okay, so this is only for incompressible. So if the fluids are incompressible, and remember those are liquids, then we can write that V1 equals V2 and rho 1 equals rho 2 equals rho. Notice that if V1 equals V2, there is a V1 or a V2 in every single term across the equation, so we can cancel them all out. And in addition, now I'm dropping subscripts on all of the rows because they're the same, and so we're not using a subscript at all. So this is the equation we come up with. And when we rearrange the equation to get all ones on one side and all twos on the other side, this is what we get. So this is the form of Bernoulli's equation that we'll be using, and this is, of course, for liquids. These are incompressible fluids for liquids. So this is Bernoulli's equation. You don't need to have a good solid understanding of how to derive it. I hope that you followed the steps. Please ask questions if you didn't, but you do need to know how to use this equation. And it's important to note that these pressures, P1 and P2, can either be the gauge pressures or the absolute pressures. They can be either one. But if you use gauge pressure for P1, then you must use gauge pressure for P2. In other words, you must be consistent. If you use absolute pressure for P1, then you must use absolute pressure for P2. All right? So please ask questions, and we will try and apply these fluid dynamic equations to some problems from your text next time. Thank you.